Hello everyone, myself Aesha K. Joshi, lecturer in Electrical Engineering Department, VPMP Polytechnic. My subject is Analog Electronics. Unit name is Field Effect Transistor. And today we will discuss about working of junction field effect transistor. So our objective is to understand how the junction field effect transistor works. Now let's discuss the operation of JFET. So for the operation of N, here we are taking N channel JFET. So for the operation of N channel JFET, VDS means the voltage between drain and source. So VDS is positive. This VDS is positive and VGS is always negative. This VGS is always negative. The conventional direction of current is from drain to source. The operation of JFET for different values of VGS is shown in the diagram. So you can see on your screen there are three diagrams for the different value of VGS. So in first diagram, it is an operation with no bias voltage, means at that time VGS is equal to 0. In second diagram, diagram B, is the operation with a small negative gate source bias. It means at that time VGS, the value of VGS is very small, negative. And in diagram C, it is about operation with a large negative gate source bias. It means it has a value, large value of negative VGS. So let us consider one by one and start with the first operation when the VGS is equal to 0. So considering first diagram where the VGS is equal to 0, here the gate is connected to source. This gate is connected to source, making VGS is equal to 0. And due to supply voltage VDS, this is VDS, current starts flowing through the channel. This is the channel and current starts flowing through this channel. The N-type material has finite resistance. This N-type material has finite resistance and therefore the drain current flow causes a voltage drop along the channel. So here this is a channel where the voltage drop causes. This voltage drop will reverse bias the gate to source junction. The depletion region of the reverse bias, here it is the depletion region, and this depletion region of the reverse biased PN junction penetrates more into the N-type bar because it is lightly doped as compared to the heavily doped P-type gate. So the penetration of the depletion region into N-type bar depends on the reverse bias voltage. And due to the depletion regions, the width of this channel available for conduction is reduced. The value of this drain current is maximum when VGS is equal to 0 and is called source saturation current, and it is denoted by IDSS, which is source saturation drain current. So this is happen when VGS is equal to 0. Now come to our next situation, next condition where we apply small negative VGS. So now a small negative voltage is applied between the gate and the source. Here small negative VGS is applied. Due to the reverse voltage applied across the gate source junction, the penetration of the depletion region into N-type material increases further. You can see in this diagram the area of depletion region is comparatively more than the first diagram, because here the reverse voltage applied across the gate source junction is more compared to the first condition, and this will reduce the channel width further. So it reduces the channel width again, and this will reduce the channel width further. Due to the reduced channel width, less number of electrons can pass through the channel, and so less number of electrons, it means less amount of current can pass through to drain from source, and therefore the drain current ID reduces with increase in VGS. So as VGS increases, the drain current ID reduces. Now come to the next condition where we apply large value of negative VGS. As the negative VGS is further increased, the depletion regions spread more inside the N-type bar. You can see the diagram here. This is the depletion region, and the area of depletion region is more compared to previous conditions. At a certain value of negative VGS, the depletion regions touch each other. As shown in the diagram, at certain value of negative VGS, the depletion regions touch each other, and therefore the channel width becomes 0 and the drain current is also 0, and this gate to source voltage VGS, this VGS at which the drain current is cut off is called VGS off. Or with the increase in negative VGS, we can say that if we increase the value of negative VGS, the channel becomes more and more narrow and the drain current reduces, and the gate to source voltage VGS at which the drain current is 0, or we can say it is completely cut off, then it is known as pinch off voltage. It is known as pinch off voltage, and it is denoted by capital V suffix P or VGS off. So it is called pinch off voltage, or it is represented by VP or VGS off. So it is the voltage at which the drain current becomes 0, and the value of pinch off voltage VP is negative for N channel JFET, and generally it depends on doping of the N and P region of the device and width of the original channel structure. So this is how the N channel JFET operates, and the operation of P channel JFET is exactly similar to the N channel JFET, except that the current carriers are holes in case of P channel JFET, and polarities of the DC supply voltage VGG and VDD are reversed in case of P channel JFET. Otherwise, the operation of the P channel JFET and N channel JFET is almost same. So you can easily understand operation of JFET by the given diagrams. So this is what I have discussed just before. There are three conditions: VGS is equal to 0 with small negative VGS and with the large value of negative VGS. What happened, that we have just discussed. Thank you.